that's better for most people in here. Okay. So yeah, so it is. It's 1:30, so we can get started. Welcome back, everyone, from lunch. I hope everyone had a relaxing time and got to catch up with folks. So the title of this session is Forecaster Priorities in Improving S2S Applications. This is part one. We'll have a part two tomorrow morning at 10:30. Really happy with this group of speakers we have come up. Great selection of talks. First today, we have with us Mike DeFlorio from the Center for Western Weather and Water Extremes. So we're really happy to have Mike here join us virtually and share the work that they've been doing on subseasonal timescales out in California. So Mike, without further ado, I'll let you jump in.
Thanks so much. It's great to get to chat with everybody, joining you from the West Coast, where we're entering into a 3-day pretty extreme heat wave in Southern California. So interesting lead up into the new water year that's starting in October currently. It's great to get a chance to talk with everybody. For those of you who don't know, I'm Mike DeFlorio, leading the subseasonal and seasonal focus area within CW3, the Center for Western Weather and Water Extremes. And like I said, it's a pleasure for me to be able to speak with you all today. I hope you're enjoying the workshop. I've been enjoying the talk so far. So I thought it'd be cool with this group and in this setting to go through some of our subseasonal research and experimental forecasting efforts that we've been undertaking at CW3 over the last few years, with a particular application to a very important winter atmospheric river family event that occurred in December of 2022 and 2023. So it'll be sort of a case study, but it's speaking to a much larger programmatic effort within the center. So I think this group is very well motivated on this problem, but just to acquaint those of you who aren't super familiar with Western US applications, the real motivation for a lot of the research that went into the case study that we'll be looking at today is that water managers in the West are really in need of better S&S, subseasonal and seasonal forecasts of precip. And a couple of years back, myself, the CW3 director, Marty Ralph, Dwayne Walliser from JPL, and then Janine Jones and Mike Anderson from the Department of Water Resources here in California, we thought it would be useful to outline that there are lead time dependent decision support needs that water managers have in the West, and they vary, right, depending on whether we're looking at weather forecasts, subseasonal, seasonal, or even out to more climate timescales. And there are also, as we know, different physical processes that can impact predictability at those different lead times. And so this is a good motivation, I think, for the problem of long-range forecasting at the subseasonal and seasonal timescales as it pertains to water managers in the West. So if it's a new topic for you in terms of that application, I would point you to this paper in EOS that we published a few years ago. And Janine Jones, who's really been a champion of advocating for better subseasonal and seasonal prediction, and particularly as it pertains to drought response in the West, she implored me to include a photo that showed a really stark picture of drought in California for this article. So this is the kind of headline photo that you'll see if you go read it. And it's the water level in Lake Oroville, which is in the northern part of the state here in California. And this was in 2015, when the water level was 52% below its historical average. So that was a period of drought in the state. And we'll be visiting another period of drought that we had in the state as it pertains to this case study from a few years ago. Just really quickly, we don't have to go through all the details of this slide, but I wanted to highlight that CW3, along with collaborators from CPC, from IRI, Lamont Doherty, University of Arizona, NASA JPL, and also NEWA, the National Water Organization in New Zealand, we've produced a suite of subseasonal and also seasonal experimental forecast products that we have on the CW3 website. So if you go to the CW3 webpage, there's a tab for subseasonal and seasonal forecasts. And during the winter season, when these products have been tested for their historical skill, we post these public products using data from NCEP, data from ECMWF as well. And so there are different quantities that we focus on. Atmospheric rivers obviously are a huge quantity of interest for the Western US. Also, we have several tools that focus on large-scale circulation patterns. So looking at the probability of different ridge types occurring at these subseasonal lead times. So just a kind of an advertisement here for some of these products that are on our public-facing website at CW3. I also wanted to call out a process that we have within our group at CW3 called our advisory panel. And this is actually the second such panel that we've had. The first panel was from 2018 to 2023 with Marty Ralph and Dwayne Walliser as co-chairs, and then some internal members at Scripps serving as members. But we really wanted to expand diversity in many ways of the panel as we look to recruit new members. And so we've recruited in Dave DeWitt, obviously the director at CPC is now a co-chair, Kristen Gerges from Scripps, Andy Robertson at IRI, Christina Stan at GMU, and then Shubin Zhang from the University of Arizona. And this group gets together quarterly with our S&S team at CW3. And basically the point of this group is to look at the forecast products and the associated research from this slide, right? The AR products, the ridging products, and have an evaluation framework and feedback opportunity from experts in the field to basically scrutinize the products and make them better. And that is not only from the research side, but also things like forecast product display, labeling of products, color schemes, things that all of the advisory panel members have had a lot of experience in terms of interfacing with stakeholders on. So this is kind of one of our internal vessels for getting research on subseasonal and seasonal topics into a forecast product that can be used and is user-friendly. That process also includes, in this case, members of or personnel at the Department of Water Resources in California, and also the U.S. Army Corps of Engineers as part of the FERO effort. They may be entrained into these sorts of processes in the future. Okay, so that's a bit of a foundational framework for what we do at CW3, how projects can go from the research mode to an experimental forecast product. So let's look at some applications now to this winter that I alluded to from 2022 to 2023. And I'll mention this article was published in BAMS earlier this year. There's a lot of co-authors. I had people call me crazy for thinking that we could, corral this much feedback into one it was a logistical challenge, but it was also really fun. And there's a lot of unique input from different institutions and really all over the globe. There were people that had input into this work. And so very collaborative effort, and just a huge thank you to all of the co-authors. Some of you may be listening in or attending this meeting. So the background for this case study, California was in a very, very significant drought heading into the water year of 2023. So basically, looking at the drought conditions from the US Drought Monitor from September, late September of 2022, you can see that 94% of California was experiencing at least severe drought conditions. And 41% of the state was experiencing extreme or exceptional drought. But by the end of the winter, just a couple of months later, towards the end of March, less than 10% of the state was experiencing severe drought, and the extreme and exceptional drought was completely gone. So I should mention, this is really from a surface perspective in terms of water. Obviously, the drought bears scars that last, beyond just the immediate alleviation of drought conditions in this definition. But still, something remarkable obviously happened during this period to help us from a groundwater perspective. And the culprit behind the real dent that was put in this drought were a family of atmospheric rivers that made landfall in a 3-week period from the 26th of December of 2022 through the 17th of January in 2023. And according to the AR strength scale that was introduced in Marty's 2019 paper, One of these was in the highest category of intensity, called an exceptional AR, that made landfall right around the Oregon-California border. So this was, the driver of the statewide alleviation in drought. This figure really highlights how it was that 3-week period in December and January that was the driving force behind alleviating the drought, not really the periods from January to March. So what this shows, this is a figure that's from that paper. On the left, you're looking at the period from October of 2019 through November of 2022. And the shading is showing you the normal water year's worth of missing or extra precipitation as a function of space. So basically, there are a couple of areas in that plot that are white, which means that those regions were basically at normal or slightly above normal in terms of the precip that fell in that 3-year period. But throughout much of California and Nevada, you see the yellows and the oranges and greens, which means that we were in an accumulated deficit of precipitation falling during that period. The middle panel is that same quantity. The shading is a little bit different, but the period is that 3-week period in December and January. And so you can see, especially in the areas near Lake Tahoe, the Sierra Nevada region, kind of bordering California and Nevada, those really dark blue shadings mean that in just 3 weeks, there was over a year's worth of normal water year precipitation that fell and primarily in that region in the form of snowfall. So again, just in 3 weeks, a huge footprint of precipitation falling over parts of California and Nevada. So then if you do the same calculation from the left panel, but you include that 3-week period, that gives you the panel on the right. And so you can see in those regions where there was that dark blue, very, very heavy footprint of precip in that 3-week period. Now, if you add that in and go back to October of 2019, many of the regions in the Sierra Nevada mountain range and also in central and extending into coastal Southern California, they've now caught up basically back to normal just from that 3-week period. So this was really remarkable, made headlines around the world. There was a lot of damage as well, in addition to the benefits of the precip. We heard this concept earlier in the workshop, right? There can be benefits, but also hazards to receiving this sort of drought relief. And the hazards in our region are typically in the form of flooding and landslides. So then part of this paper was the diagnosis of that remarkable period and what was observed. And then part of it was about evaluating some of these experimental forecast products that we've created at CW3 with our collaborators, looking at subseasonal prediction. And this is one such forecast. I'll walk you through what each row is. If you just focus on the top row, this is a multi-model prediction using data from NCEP, also ECCC in Canada, and DCMWF, plotting the anomaly forecast for week 3 for atmospheric river activity. And then the right column is the observed or reanalyzed data from ERA 5. So any region in those forecast plots where you see blue, it's indicating an above normal probability during week 3 for atmospheric river activity. So you can see that in all 3 of the models, with differences in the precise landfall location or intensity, all 3 of the models were picking up at week 3 lead some signal of enhanced AR activity over California. And obviously that verified as the valid period here was the 23rd to 29th of December when these ARs started to make landfall. The other rows are different week 3 valid periods going into early January and late January when the AR activity persisted and then eventually acquiesced. But so part of this paper is looking at, okay, the models actually did a really good job in this case of capturing a large scale shift from the ridging and drought conditions that we were experiencing in the beginning of the winter to this heightened AR activity that we experienced. But critically, there were, part of the paper goes through some of the errors as well. There were errors in things like inland penetration of AR activity and also landfall location. But I would say overall this was a success story for the dynamical models in capturing the shift into record wetness.
Hi,
And then
Mike.
hey there, yeah, this was the last slide.
Okay, great. Fantastic. Thank you.
Okay, yeah, and then just to wrap up, a big part of this paper and a huge effort that we've undertaken at CW3 in the last few years is the creation of forecast synthesis tables that summarize this sort of forecast data at subseasonal leads across different models and different regions along the Western US coastline and even into the interior. And this is an example for this case. You have week 2, week 3, and week 4 in each row. And you can go through the paper in more detail, but basically this is a visual tool that CW3 now includes in our weekly wintertime subseasonal outlooks, where even if you don't look at the individual forecast products, you get a sense of how the odds are tilted towards above normal, below normal, or near normal precip based on these tools that look at air activity, ridging, etc. And so you can look at the paper in more detail for this. I've summarized most of this. I want to be respectful of time, but really appreciate the opportunity to chat. And thanks to all the collaborators for helping make these ideas possible, and looking forward to interacting with some of you in the future about how to expand on these ideas. Thank you.
Thank you, Mike. That was a fantastic talk and remarkable winter for sure. In the interest of time, we will move on to the next talk. I encourage folks to reach out to Mike by email or through the Slack channels if you have questions or want to discuss things. Our next talk, invited speaker, Jon Gottschalck from CPC. He's the branch chief of the prediction branch chief. And he's here today to talk to us about CPC's climate outlooks and our forecaster priorities. Can't see that. Yes, so I will set you up here real quick. So I'm going to exit full screen. And that should stay on. There, okay, so I need to share the screen. Like this. I'm going to control it.
Okay, great. All right. Thank you very much, Corey. Thank you for the organizers for giving me the opportunity to speak today. As Corey mentioned, I'm Jon Gottschalck. I'm chief of the operational prediction branch here at CPC upstairs. And although my name is on the author here, this content of the talk and many of the preparation of the figures and products, of course, by many different folks. So just wanted to note that. Just a quick outline. Many of you are familiar with what we do at CPC, but just a quick mission statement and an overview of our products and services. I want to give some example applications as some of our speakers have. Go through quite a bit some of our challenges and model guidance dependencies for this, the focus of the meeting. Some forecaster feedback and priorities first with the seasonal, and then later on with the subseasonal. So just very quickly, for CPC folks who are not familiar, deliver real-time products and information that predict and describe climate variations on timescales from weeks out to about a year, promoting effective management of climate risk and a climate resilient society. You can see just from that mission statement, our mission and objective is incredibly broad. From say the week 2 low end of the subseasonal time scale all the way up to multiple seasons to next winter, next summer, things of that nature. We have both a very strong domestic and international presence, both monitoring, assessment, and predictions. And a very huge part of what we do, obviously, is the monitoring of major climate modes, surface conditions, which will really play a large role and help us prepare the outlooks. Overall, and you can see some of the examples of some of the types of products there on the right, but also listed on the left-hand side with respect to a lot of the major climate modes, both on multiple timescale, subseasonal and seasonal. Some outlooks that have been shown already, just trying to give an overview here. For the subseasonal range, we have our week 2 outlook in the upper left, for example, for temperature and precipitation, week 3 and 4 on the bottom right. Which is relatively more new in the last 10 years or so compared to some of the other products. Also our seasonal forecasts, temperature and precipitation, and our week 2 U.S. hazards outlook in the bottom, So we also focus on extremes, and we're looking to move forward with priorities to extend this into further into the subseasonal time range and investigate potential on the seasonal time scale. But right now, these are our current operational products. Other products targeting various phenomena, for example, our Global Tropics Hazard Outlook, which targets obviously the tropics related to impacts of whether it be weekly excessive rainfall or extreme heat for pre-monsoonal periods, extreme rainfall for atmospheric rivers, bursts or breaks in the monsoons, for example, and of course, tropical cyclone activity across much of the basin. This is a week 2 and 3 product and it's probabilistic. Noted earlier by Hylin, we have our monthly and seasonal drought outlook on the upper right, which is a tendency for what conditions will be at the end of the period, and our ENSO outlook for one of the 3 phases of ENSO neutral, La Nina or El Nino on the bottom. And all of these products have different cadences, launch schedules, and operational tempo. Some applications very quickly, because I think it's really important, and this has been emphasized already. On a shorter time scale, there's many sectors, obviously, I think everyone's aware of, that use these products for S2S. It's actually, in my branch, many of my staff and myself are kind of on the front lines of interacting with a lot of stakeholders, and so we see these application needs and just the need for all kinds of information on these timescales for real world decision making and increasingly longer lead times, whether it be week 2 here for the energy sector wanting to know cold air, extreme cold air outbreaks. We try to do that in some ways with as part of our IDSS initiative in the Weather Service, through which are known as key messages, which is an example on the right, where we're trying to get more to the real impacts of what our forecasts are trying to say. This is an example of really the one major extreme cold outbreak we had this past winter. And the reason for this, of course, is the staging of resources, opening of shelters and so on to help mitigate losses. I've always mentioned the economic benefit of the Weather Service mission. CPC really fits heavily into that, and it's often overlooked. From the subseasonal last year, we had a very warm winter. We had a huge green up across much of the south. This is something more on the week 3 and 4 time range for a pattern change. This example was a key message that we had where we expected a colder outbreak, where we're looking at all the things we're talking about at this meeting, MGO, the stratosphere, and ensemble model guidance, which was overwhelmingly consistent with we're gonna have a major pattern change with impacts. And we had some of the plots here on the bottom left are the freeze warnings in the southeast. There's major losses to crops, basically a complete loss of the peach crop across parts of areas of Georgia and so on with this. And some people were able to identify this, utilize the information, and make some decisions to help mitigate the economic losses. And finally, going to the seasonal time scale, getting back to also what Royce was mentioning earlier this morning, is that with respect to the flooding and also water supply issues, we also have a number of stakeholders that are wanting to know longer range, obviously, seasonal impacts of precipitation. This was a case in 2019 where we worked with Central Region on flooding issues, but also crop planting, getting in the and just the wet conditions through much of the summer. And it really had a large impact on crop planting and actual yields, where we provide regular calls on our seasonal outlooks and also our shorter term outlooks throughout this with the U.S. Army Corps of Engineers and other stakeholders such as the USDA. So, a lot of challenges, obviously. There's a lot of text here. I'm just going to focus on a few of these, but for completeness, I'll leave this up here. Kind of grouping the first 2 or 3 together, in that obviously our outlooks are probabilistic. So we require a lot of multiple sources, echoing what Bill Merrifield said earlier this morning. I really need to use that multi-model ensemble approach. Large ensemble suites are important for us. And critical, absolutely critical, is the consistency and robustness of reforecast data sets that are basically an effective configuration or similar configuration to the real-time forecasts for a lot of reasons. Consistent initial conditions, skill estimation, ease of processing. We operate in a low, as everyone knows, in a very low signal to noise environment, unfortunately. And so our efforts have to be targeted, and we need to know when that can occur, and reforecasts help us do that. Other areas here include just the interpretation of probabilistic forecasts. We've done a lot with social science recently, but that still remains a challenge, as was noted earlier. And finally, we're working towards extremes, so we need additional model data that capture the maxes in some of the model output time periods as opposed to instantaneous values within the synoptic times. Model dependencies, I'm not going to spend too much time on here, but as was noted earlier, we use the NMME and the Copernicus seasonal outlook suite. Those are all listed there. And on the right-hand side, just an image that some of our forecasters look at each month and doing the seasonal outlook. But we obviously do a lot of post-processing at CPC. So the reforecast, model reforecast methodologies are huge. We do not only systematic error removal, of course, based on that, but also we have a number of different calibration techniques that we use. And this doesn't include a lot of the statistical or hybrid type techniques that we utilize. But also we'll be moving into, like everyone else, machine learning and AI type, whether it be through calibration of the forecast or specific tools. Subseasonal, same thing. These are the model forecasts that we use, the CFS, the GFS, the Environment Canada's Global Ensemble Prediction System, JMA, and the European Center. These are some examples here, forecast things as well. And a similar sort of paradigm is being used here. That should say ensemble regression, not probability anomaly correlation, but we are working in that area as well. As far as forecaster feedback and priorities, I'm not going to mention all of these, but a few that are important to highlight. One, as was kind of noted earlier, I think a few times, is the decadal trends in these models are too robust. We're extremely strong on the warm side, of course, and also ENSO impacts are biased somewhat strongly too, in the sense that even more weak or moderate type events sometimes come across as strong events in the forecast probabilities. We have the same issue, especially with the CFS, false alarms with the ENSO starting points, whether it be El Nino or La Nina. This is an example from earlier this year and these are all the models, not just the CFS from earlier this year, where we'll be more in La Nina conditions by this time currently. It's been slower to evolve than what we've seen. And the plot on the left is just the summertime temperature trend through an OCN approach. And the idea is that the trends shown there are much less for many areas than what's shown in the model and the mini model. So it can create problems with respect to identifying where to forecast below normal temperatures. It doesn't happen very much, and we don't have much skill in doing that right now overall with respect to the 30-year base period we're required to use. And a few other things that are noted there, sensitivity and jumps in initial conditions. As far as this slide for the CFS, just a few things to note here, because I've already touched on some of these, is that for us, the resolution really needs to improve from what we're currently using. And that's been noted earlier as well. Even though we're dealing with climate modes, an increase in resolution would be helpful, we believe. The reforecast configuration, as I mentioned earlier, would be best to have a number of members at one synoptic time as opposed to scattered throughout the day, 24-hour day, as was with the current CFS. Longer reforecast periods, we understand that that's difficult, but it will help us with the decadal trend problem and also for machine learning and AI type methods. And also when model upgrades occur, it's really important for us to have that real-time configuration in terms of initial date and time, ensemble size, et cetera, provided 3 months in advance so we can have a good set of testing before we implement the new model forecast into our operations. And as mentioned on the bottom there, the longer reforecast day would be preferred, but we understand that there's IT limitations. With respect to the subseasonal, there's a few that I want to mention here that are not really related to some of the others, is that the one that hit us very hard last year was the very warm bias in the GFS across much of the central US and some of the extreme heat events. I know that that's been addressed and will be implemented in the next release, I believe. But also, again, some of the things that we have problems with are targeting below normal temperature anomalies, even with the GFS in the shorter time range. And the main one I want to target on the subseasonal here is that what we see with the GFS at times is a difficulty in the forecasting the height pattern across much of the North Pacific and into the US. And this has been known and discussed with folks, our colleagues at PSL and so on as well. So there's definitely a tropical, extratropical teleconnection issue with the GFS, similar was noted earlier this morning. Last, before I go to my final summary slide, one critical thing for us is for our monthly forecast, we would like to have an extension of the GFS system to be able to cover both outlook releases the mid-month and the update, which would require more than the 32, 35 days for the period, or along what the European Center has, on the order of, I think, 46 to say 60 days or so. That would help us in that case. Also, as I mentioned, the same requirements for the reforecast information, but also for extremes, we're trying to move more and more aggressively into the subseasonal with extremes, focusing first on temperature, where we think that may be more predictable. But we need that information, the max information between 6-hour periods for us as much as possible. And this is just an example of our week 3 extreme heat forecast from the different models, in this case, the GFS, the European, and the CFS. And you can, these are probabilities for the week 3 weekly mean being in the upper 90th percentile. And so you can see lots of variability there between the models. And so there's a lot more bias correction, calibration that needs to be done. We are working in that area. And so last slide, CPC delivers a broad spectrum of operational monitoring and outlook products, as I mentioned, including extremes. Can't stress enough the range and of applications for this time range that we hear about pretty much every day. We have obviously inherent challenges given the time scale we're dealing with as far as predictability. Some things inherent non-predictability, certain seasonal dependence as well. And for us, we really have done a lot to try in the last few years to improve the interpretation and understandability of our products through social science to maximize the benefit of our operational outlooks through climate education. And finally, we're doing a lot of applied research in both branches for product development and to further advance skill, of course, but also product scope. And that was mentioned earlier. We are moving, we do have probability exceedance information for our outlooks and on a grid that we're developing. We just in the process of finishing that up and releasing that, so that sort of information plus heating and cooling degree days in week 2 and further on, as well as other types of products that we are working in the subseasonal range that we hope to move forward with over the next several years. So thank you very much for your time. Appreciate it. Thank you.
We have time for one quick question. Okay, drop it up, John.
Yep.
So our next speaker is Wanqiu Wang from CPC as well. He's the monitoring branch chief. He's here today to talk to us about improvements that CPC is seeking for the seasonal forecast system and for seasonal prediction products. Thank you.
The same file.
Huh?
Same file.
Same file. Oh, sorry. Oh, I just keep going. Oh, great.
Keep going.
Okay. Yeah, there you go.
All right. Yeah, I think one of the key messages from Jon's talk is that we need a good forecast system. So here I will focus on seasonal forecast system, and I'll start with a question: what make a good forecast system? Seasonal forecast system. Obviously, everybody knows the answer. We need good initial conditions. We need a good model. But specifically for seasonal forecast, we not only need accurate initial condition, we also need consistency in temperature consistency in initial condition. And for the model, we want the model to capture the skew sources that include the long-term trends, and so magnitude oscillation and other low-frequency modes. And also we want the model to capture the evolution of surface conditions and atmospheric model response to the condition. Now, what deficiencies are now in the current forecast systems. In the past years, quite a few deficiencies are identified in CFS and AMME models. I'm not going to talk about all of this, but we'll focus on 4 of them, which are long-term warm SSD trend errors in tropical Pacific, and also false alarms, and temporal discontinuities in initial conditions, which John also mentioned, and also MGO propagation, slow propagation. So starting with the first one, which is long-term warm SSD trend errors, I borrowed this from Michelle Lu's analysis. I know Emily Becker also did similar analysis. Here, we see the analysis for 8 AMME models. We see that warm SSD trend errors are seen in all 8 models, and particularly in CFS and CCSM4, the warm trend errors start even in month 1. And where in other models, the errors are more clear at the later lead time. So the impacts of these trend errors include ISO amplitude bias, an increase of false alarms, and the trend errors in precipitation in the tropics, and also teleconnections due to the displacement of tropical forces. So what are the causes of these warm trend errors? There have been a few studies on this that include sensitivity bias in the model to radial forcing, and lack of the representation of interaction between Southern Ocean and the tropical Pacific, and also the need for high resolutions for both atmosphere and ocean. Here, I want to share with you our recent analysis on the impact of initial conditions. So here we compare experiments using UFS prototype 8, initialized from 2 sea ocean analysis. One is from ORAS 5, and the other is from CPC's GLERL analysis. And the red panels are CFS version 2 for reference. So when the model was initialized from ORAS 5, we see the warm trend errors as in other current forecast system. And when the forecast was initialized from GLERL, interestingly, the trend errors are less clear. So this means the initial condition, ocean initial condition, could be another reason for this tropical SSD trend errors. You can see more details in Yang's poster, which is already there. So next, I want to talk about the ANSO false alarms. Starting with some specific cases, here is CFS forecast. The blue curve is observation, and the red, blue and the red curves are forecasts from CFS. We see that CFS issued false alarms for 2012, 2014, and 2017. And this false alarm problem is actually common in many other models, or if not all models. Here, I'm showing a recent analysis by Levine for 6 AMME models. What he found is that the AMME models issue too many high confidence El Nino forecasts during boring spring forecast. He also looked at the relationship between the false alarms and the subtropical SST anomalies. And he found that corresponding to the false alarms, there are negative SST anomalies in northern subtropical Pacific. This this result is actually consistent with our MEP simulations we carried out a few years ago. Here we compare the MEP simulations using CFS with 3 different convection schemes. Here, upper left is observation. The shadings are SSTs, and the contours are zonal wind stress. And for MEP simulations, we have simulation with SAS and SAS2. SAS2 is the current scheme in CFS, and another scheme is RISE. When SAS and SAS2 are used, the model produced strong westerlies, which would enhance the existing SST anomalies, warm anomalies, resulting in false alarms. And when the RAS scheme is used, the wind stress is very similar to the observed. So with the RAS scheme, the model is less likely to produce false alarm. So what this suggests that using MEP simulations forced with observed SST can be helpful to understand models representation of VSC coupling. By the way, this is for particular year 2012, and we see the negative SST anomalies in the subtropical Northern Pacific. So then another thing I want to talk about is discontinuities in the initialization system, which John also mentioned. We have seen this here or there, but I just want to spend a couple minutes on this because this is so important. And also, this is probably more like a technical issue, so it's probably easier to resolve than others which are more science issue. So this discontinuities are found in all components in the coupled system, land, ocean, and sea ice. So here we look at the soil moisture anomalies, zonal mean soil moisture anomalies in CFSR, which is used to initialize CFS. We see that the jumps between streams for the historical period, and in particular, when the system was implemented in 2011, we see a jump to wet conditions systematically for the whole period. This wet anomalies resulted in soil moisture anomaly in the forecast, and also corresponding to the soil moisture anomaly, we have cold temperature anomaly. So this is land surface. We also have similar jumps in ocean. So this is ocean temperature difference between CFSR and the TAO. We see in 1998 there's a jump in the differences, which becomes warmer. This resulted in the jump in forecast ST before and after 1998. This caused a lot of headache in our forecast post-processing and also for diagnosis of model forecast. There's also issues in sea ice, which I want to skip for now and move to another even simpler one and more recent one, which is use of a different SST analysis. So CFSR use SST analysis to maintain a reasonable sea surface temperature. From 1982 to 2019, OSST was used, and after 2019, another SST analysis has been used, which is NSST. So here we look at the we compare the linear 34 SST with other three analysis, OSST, OSTI, and ERSST. So NSST is consistently cooler than other analysis by 0.3 or 0.5 degree. And interestingly, we also see the forecast ST is consistently cooler than the observation. So here is CFS 2 forecast, and the circles are the observation. So we see the forecast is cooler. This doesn't necessarily say the NESST is the reason. But at least we should minimize this type of discontinuity. So next, I want to spend a couple minutes on MGO. MGO affect subseasonal forecast. It also important for seasonal forecast. It affects ANSO. So a major deficiency is that the MGO propagate too slowly in most forecast models. Here, negative phase error means slow propagation. And the red diagram is CFS forecast. The blue is observation. Red is forecast. We see that the model forecast propagate more slowly than the observation consistently. It doesn't matter where the forecast was initialized, and also the amplitude is weak. So, so before I stop, I want to share with you some progress in the new GEFS 13. Here's the forecast from Dynamo for November 2011 MGO event during the Dynamo period. Observation shows a nice eastward propagation. And GEFS 12 propagate too slowly. CFS version 2 propagate too slowly. And both ECMWF and GEFS 13, which is labeled as EP5R2 for now, both are much better, even though the GEFS 13 is still slightly too slow. So, but anyway, this is encouraging. We see the improvement in the GEFS 13. Tomorrow, you will have we'll give a presentation on this, so we can see more details tomorrow. So that's basically all I have. So again, there are a number of existing issues that are highly desired to be addressed. Correcting any of these errors will result in improved seasonal forecast, especially for temporal discontinuities. We really want to do everything we can to minimize the discontinuity or even avoid these discontinuities. Thank you.
Do you have time for a question? Okay, thank you, Wanqiu.
So our next speaker is Mark Klein from NCEP WPC. He will talk about the WPC's increase in use of S2S prediction tools and data. Mark, please.
So good afternoon, everybody. I'm Mark Klein. I'm the Science and Operations Officer for WPC. He's already read our title slide, so I don't need to really go into that. But who are we? Similar to OPC and CPC, WPC is a national center with forecast responsibilities and is also housed here, actually up on the 4th floor. So you can read our mission statement, but in a general sense, we have a very broad product suite and can be sort of considered as like the foundation for the nation's big story weather picture, generally in the day 0 to 7 time frame. We do have some areas that we tend to specialize in. Overall, one is heavy rain and flash flooding events. We've actually been putting out QPF since 1960. So we've got a lot of experience in that area. We've had a national winter weather desk for over 2 decades and are actually getting more involved with watch collaboration for the field. And more recently, we've been focusing on extreme temperatures and the prediction of them and creation of key messages, especially the heat that we've seen the last couple of years. But so we cover all 50 states. We have an international desk that produces IDSS for the Caribbean, Mexico, and South America. And while we don't really work in the S2S world so much because our product suite ends basically at day 7, we are very interested and use the GEFS considerably as we are a leader in the probabilistic aspects of QPF and winter weather. So we really are interested to make sure that the GEFS is, whatever requirements that we can provide, we want to try to get those out there. So just kind of go through a few bits of our product suite here. I would say the most significant use of the GEFS and ensemble guidance in general is going to be the medium range, or day 3 to 7. Within about a year or a year and a half, we're going to be the official forecast for the Weather Service in the day 4 to 7 period. So definitely going to be utilizing the GEFS heavily, and it's going to become considerably more important. But the additional focus really has been, and I keep going forward with this, is the prediction of hazards. It's not just the actual, whatever the conditions might be, but we're really focused on hazards and impacts. So we have an example there of a probabilistic heat index forecast that's from the GEFS. Another area where we've worked very heavily in the last several years is the development of ensemble clusters, trying to pull some more information out of the ensemble data by being able to create different scenarios that we could message to partners. On the right-hand side is the winter weather. This is a probabilistic winter storm severity index. The winter storm severity index essentially takes MD/FD forecasts of winter variables and combines them with non-meteorological factors to really focus on the aspects of impacts to society of winter weather. So snow load, things like flash freeze, blowing snow. And this probabilistic product that goes out from day 0 to 7 is heavily using the GEFS out past day 3. Talk a little bit about QPF. We use ensemble clusters for that. We have plume diagrams we access the GEFS with. And then again, with QPF, one of the factors is trying to look at what is the probability of exceeding something that's impactful, not just a 1-inch or 2-inch threshold, but flat flood guidance or an average occurrence interval, or something that we can, put a definite, stamp on an impact. So that's that figure in the sort of the middle with the purple. Another probabilistic product we create is excessive rainfall outlook, and it is the one product we have a machine learning tool that was developed by Colorado State University that was trained on the GEFS reforecast and uses the GEFS. I'll go into that a little bit more later, but this provides a first guess for our forecasters for this product, and has really been popular. Additional tools, which again use the GEFS, the Ensemble Situational Awareness Table is a product that was developed, or tool developed in Western region, and really just trying to provide a climatological context to different variables in the ensemble mean. So it's comparing the ensemble mean forecast to the CFSR over it looks like a 30-year period. And really, here's just an example from last year. This was Hurricane Hillary, and some of the ensemble situational awareness plots there are the integrated water vapor transport and the PMSL. And so in both of those cases, this was outside of the climatological range for this period. So it's a really good tool to get a quick look at where there might be high impact events over the country. Now, we only do forecast to day 7. We had extended our forecast process into the day 8 to 10 round for several years. We had an extended range forecast experiment, and it was again really focused on probabilistic forecasts of temperatures, extreme temperatures, heavy rain, heavy snow. So that while that did end, it really helped launch the development of the cluster work that you saw a couple shots of there. And also, we currently provide the day 3 to 7 hazards forecast, which was previously done by CPC. We took that over about 5 years ago. And a lot of the tools that were developed in the extended range forecast experiment are used back in that medium range period for the day 3 to 7. So I just want to go a little bit more into this AI tool. It's a random forest technique that is trained on the GEFS version 12. It's actually been around since 2017. So the first iteration of this was trained on V11. And essentially the goal of this product, and it's gone through several iterations through our hydromet test bed, is to provide a first guess for our forecasters for the excessive rainfall outlook. It's trained on flash flood reports, exceedance of flash flood guidance, exceedance of average occurrence intervals, and there are different predictors along with QPF. There's CAPE, precipitable water, PMSL, and a lot of the work is, it's not just a full CONUS thing. The country's divided into sectors because certain areas have a different type of climatology and different factors affect the heavy rainfall. So it's just an example from Debbie a few weeks ago. The plot on the left is the first guess field from CSU. The middle plot is WPC's excessive rainfall outlook. So, and then on the far right is the WPC forecast overlaid with the observations. So again, the flash flood guidance exceedance or local storm reports of flash flooding. So we found that this is really a useful product, and it's provided information. It's actually run out to day 8 right now, so it does kind of help us through our day 3 to 7 hazards forecast. The question is it any good? So I looked at the verification for the last year. The gold bar is WPC. The full color bars on the left are various flavors of the CSU. The only one currently running is the 2022 version, since that's the only one that's trained on GEFS v12. And basically, you can kind of see this is essentially kind of like a reliability diagram. Our product thresholds for excessive rainfall are denoted by the green and red lines. So like for marginal, it's a 5 to 15% chance. So essentially what this is showing is fractional coverage of the forecast versus the observed. And if you fall within that boundary between those lines, you basically have what we consider a reliable forecast. And so the CSU product over the past year has done well. And I've shown this before in previous talks. So it's not just this past year. And then a couple of years ago, a study was done by CSU looking actually at the skill of this product out to day 5, and we definitely, they were able to show that their skill even over WPC's excessive rainfall outlook in that period. So kind of turning more toward what we want to focus on as sort of requirements or issues or challenges with the GEFS. I do want to give a shout out to YJ's group. I stole/used some of the work that they did with their GEFS GFS project from 2023. A couple biases that I just wanted to highlight. One is the warm bias that tends to exist in heat waves. This example was from California last year. The graph on the left is recent verification from EMC's verification service, showing the mean error or the bias of 2-meter temperatures across the southern part of the CONUS. There's a lot of lines there, but the main one to focus on is the black solid line, which is the GEFS. And you can see, although the 0 line is a little hard to see on this plot, basically almost every day in that month, which had a lot of heat, there was a warm bias in the 2-meter temperatures. Something that's been noted quite a bit by SPC is a tendency for a low CAPE bias. On the right is just an example from a couple weeks ago. A 60-hour forecast. In the middle panel, the right panel was the 0-hour, not the analysis, but essentially the 0-hour forecast. And so this was not really an issue where the synoptic situation was bad. It was just a very low CAPE bias there across the central part of the country. And on the left-hand side is a similar plot from the EMC's verification group, and this is showing CAPE verification, frequency bias of CAPE greater than 500 joules per kilogram. And this is over a 3-month period ending August 19th. And again, the focus there is the black line, and basically almost every day of the warm season, the GEFS has a low CAPE bias. So just kind of going into some of our overall requirements, I think that this was outlined a little bit by CPC and by Logan from OPC. What we can do a lot of post-processing and create probabilistic hazards associated with, you know, various thresholds like heat index and so forth. But it'd be a lot easier if something like that came out of the model directly, since our compute power is fairly limited. So just requesting more post-process variables directly out of the model. That would include things like probability and local probability matched means, which would really assist our QPF group. There's been a lot of talk about reforecasts. I don't want to necessarily go into that anymore. I think that the requirements outlined by YJ and by Jon fit ours. We definitely are very supportive of a really robust reanalysis. And I think what was previously mentioned is that there still is, it's not as much of a problem as V12, but there still is a bit of an under-dispersion issue that we want to keep focusing on with the upcoming GEFs. Finally, and again, this I did bring up a couple of these biases already, but this is also courtesy of YJ's group. A couple other areas that we would like to focus on, especially for WPC, is the poor handling of shallow cold air masses. They get broken up, or basically they get mixed out too quickly into GEFs and GFS. That progressive synoptic scale mid to upper level features, that's been a kind of a mainstay for quite a few years. And then not necessarily something for the GEFs, but it's we really appreciate the work EMC's done with that verification system that they stood up. But of course, you know, you do something good and you're just going to want more. And yes, right now there's a fairly limited amount of time that you can get stats for. So being able to pick our time, get longer duration versus 30 or 90 days, and then other probabilistic metrics would be great to have, like reliability diagrams. And then the last thing I wanted to point out is EMC's model evaluation group. I did a really, really good evaluation of GEFS V12. I was on this team. I think it was led by Jeff Manikin. I think Logan was on it. I know he did a lot of work with it. But we had graphics of case studies, comparisons between the GEFS V11 and 12. We had verification stats, multiple presentations. It was a really, really, probably, you know, I've been in the Weather Service a long time. I've done a lot of model evaluations. This was probably the best one, and it felt the most thorough. So a repeat of that for GEFS V13 would be awesome if that's possible. And that's it.
Okay, thank you.
So our next speaker is David Wright from OLR GLERL. David will talk about subseasonal-to-annual net basin supply and water level prediction for Great Lake region. Please.
All right, thank you. Okay, so we're going to shift gears a little bit here. Instead of looking at more of a regional or CONUS, we're going to shift down to a very sort of sub-regional look at things here in sort of water level forecasting. And before I begin, I need to thank my co-authors on this. They're the ones who did most of the work on this. I'm just the one who gets the lucky job of presenting it to you today. So if you've seen any talk about the Great Lakes, you've seen them all. We all have to introduce them. Just to give you some context here, again, this is sort of a home to about 34 million people across both the US and Canada. So this is a binational entity that we are working with here. Again, they contain about 20% of waters. The Earth's fresh water supply is within the Great Lakes region. And also they have a combined surface area about 244,000 kilometers square. That's the same area as sort of Connecticut, Massachusetts, New Hampshire, New Jersey, New York, Rhode Island, and Vermont combined. So when we talk about lakes, they are lakes in the sense that they are fresh water, but in scale and size, they are much greater than that. And I think it's important to sort of remember that, especially when we're talking about these models going to higher and higher resolutions. We're going to start resolving these more, and you're going to start to see bigger and bigger problems come out of that potentially if resolving these features are handled with care. And so just to give you a little bit of context here, we have a good understanding of sort of the lake's influence on the atmosphere itself. It's been highly studied. It's been extensively in Scott and Huff 96. They showed that sort of in the summertime, you have about 1 to 3 degrees C cooling downwind of the lakes and about a suppression of about 50 millimeters of rainfall if the lakes were not there. Flip, if you go to the winter time, obviously the warmer lakes gives you these lovely lake effect snow bands here, which increase the precipitation downwind of the lakes and also raise the sort of temperature by about 1 to 2 degrees Celsius. So strong influence there. The other thing is, though, that they influence sort of the progression of storms. In basically the ice-free season, extratropical cyclones tend to accelerate as they enter the region here. So there's sort of a path of least resistance that they like to follow here. So this is sort of something that we kind of look at when we're evaluating these models and how they're resolving these lakes is, are they capturing some of these features? Now, on the flip side, the atmosphere's influence on the Great Lakes themselves is not well documented, or rather it's not well quantified. We have a good understanding of sort of the process bases here that influence the lakes themselves. We understand how sort of ice formation occurs from polar air coming over the place, basically that 2-meter temperature, or that air temperature is what really controls the ice formation there. What's not really well understood or quantified then is sort of the response of the water to sort of extratropical cyclone frequency and placement, and how teleconnection patterns may influence that. We're working on a project right now. Jamie Ward, one of the co-authors here, is in prep of making a paper here. Showing on the right side, I apologize for the shading here for those in the room. It's not very clear, but on the left is basically evaporation from the lakes themselves, red being positive, so water moving away from the lake surface here. From the ERA 5 on the left, CFSR on the right. As you can see, they do a pretty good, they're fairly comparable to each other in terms of evaporation from about 2014 to 2019. You may ask why we choose that time frame. It's because ERA 5, there's a little bit of a problem with representation of the lakes basically from about 2013 before, so we cut it off there for that. But getting back to what we're looking at here is basically the response of lakes to changes in sort of atmospheric processes and atmospheric conditions. And when those change, that results usually in changes in your water level. So what we're showing here is basically the agreed upon water level from the U.S. Army Corps of Engineers here for each of the lakes. Top lake is Lake Superior. Next one is Lake Michigan-Huron, Lake St. Clair, Lake Erie, and finally bottom there is Lake Ontario. And these are changing on a seasonal basis about 10 centimeters, tens of centimeters. It may sound small, it may sound insignificant, but there are consequences to the coastal communities here for that. I'd also draw your attention to the bottom row here. This is Lake Ontario. You may notice somewhere in the late 60s, early 70s, that fluctuation is pretty consistent. That's because outflows from Lake Ontario are heavily regulated and diverted there. So there's a human component into all this when we're talking about lake levels themselves. And so really when you're forecasting lake levels, it's a really simple equation actually. It's basically just looking at sort of the delta S here, which is going to be the change in your water levels. For each of the lakes is going to be modulated by the inflows and outflows through connecting channels into the lakes themselves. Precipitation over the lakes, evaporation from the lake surface itself, and then finally runoff from the surrounding area into the lake. That's all that's going to control that. Now, very simple equation, can get very complicated very quickly here. Basically, what we will also, well, I'll be talking about for most of this talk is net basin supply. This is what we consider to be the sum of precipitation, evaporation, and runoff. Basically, this is all sort of your natural flows of water into it from the outside area. And directly observing these variables is a little challenging. We are basically on a data island when we talk about the Great Lakes. We don't have a whole lot of observations lies, especially precipitation over the waters themselves. But forecasting these variables and the MBS itself can help predict water levels and aid decision-making. So to do a better job of that, we are partnering with sort of the Army Corps here, who is in charge of doing the forecast for the Great Lakes themselves. They are the operational home of the forecast. What's showing here on the right here is basically the solid red line is your agreed water level for the past about 18 months or so. And then on the right side there in 2024, the sort of shaded area there is going to be your water forecast and basically your spread of uncertainty there in your predicted forecast. And then there's persistence in there and things like that. So they use several different models to predict this flow. Persistence is in there. There's several other sort of statistical models that are used in that. And basically the big users of these forecasts are sort of the Great Lakes water level, Great Lakes water managers, recreational boaters, shipping and navigation, basically any sort of coastal communities across the region there. And so we wanted to take that information that is being generated from our atmospheric models and from our forecasting systems here and apply it now to the water level forecast itself. A lot of this information isn't getting into the forecast directly at this point. So we're looking to sort of improve that forecast and that forecasting method here. So we're looking to use a data-driven model, aka machine learning and AI, to take input from the CFS and forecast then water levels or net basin supply from this. And what I'm showing on the right here is just the land mass in 0.25 degree resolution for CFSR. We can resolve the lakes. They're there. It's very pixelated, but they're there. Again, so the goal of this is to then extend that forecast showing earlier out from 6 months to now 9 months to a year, where now they can start to really take that information and make decisions with it that are going to impact things for the region. I should mention that all this work is being funded through sort of the bipartisan infrastructure legislation. And so taking a step back for a minute here, I want to bring up this idea of the minimum viable product. When we started out this project, we were basically given a blank slate. This had not been done before. We had no sort of idea of where to go with this. So our data scientists in this project brought the idea of sort of the minimum viable product, or the MVP. Basically the idea being to build this system, this data-driven system in chunks. So the top row is sort of maybe what you might think of doing something, where you start with, a tire, then you add some axles to it, but then that doesn't work, doesn't get you what you want. Eventually, through many trials and error, you can get to a car. We want to take this a little more in chunks, a little more piecemeal. So we're going to go with the bottom row here, where it's basically you start with building a skateboard. That's easy, that's simple. We can get that. It gets you from point A to point B. Maybe not well, maybe not fast, but it does get you from point A to point B. And then you start to add components on top of that. So then you can get to a scooter, bicycle, motorbike, eventually getting to the car. So it's this idea of let's take the most simple process here first, let's get that well, get that right, then let's start adding some complexities on top of that to get to maybe an even better product in the end. So I'm happy to say that we have an MVP working. We are in the skateboard phase right now. This was very last minute to get it into this presentation. So that's what I'm saying, just at the nick of time. But basically our process right now is we have a pre-processing step, which is going to be taking in the CFS data. It's going to be pre-processing that, doing some aerial averaging over the lake surfaces themselves. And then it's going to be feeding them into the precipitation and evaporation from the CFS into our Gaussian process model. That's a machine learning AI. It's been trained on CFSR from 1979 to 2010. And then output from that gives us a net basin supply. Now, like I said, it is very simple. It is not necessarily a robust model, but it is a model that can start to have some value to it. On top of that, we are looking to sort of connect this to routing and regulation models. These are the ones that are going to be determining how humans make decisions on how much water should be outflowed from both Superior and Ontario here. That's really what's going to drive a lot of basically the Ontario flow, and then also the Lake Superior water levels themselves. The interesting thing, though, is that these routing and regulation models show improvement for most of the objectives. Those objectives being sort of shipping, there's a little bit of regulation in there, or excuse me, recreation in those models from basically a perfect input. So if you can give a perfect forecast into these systems, they might be able to sort of improve the routing and regulation here. So there's some deeper levels here that still need to be explored to get this fully working. But like I said, we got this in just in the nick of time. So this is the first results of the MVP themselves. On the right here is just the net basin supply in terms of millimeters for about a 9-month forecast here from August to May. As you can see, it shows what you'd expect to be a seasonal cycle in this, where you're having sort of a reduction in that net basin supply during sort of the later winter season of January, February, and March there. Higher ones in sort of that late fall time period where you're getting a little bit more precipitation coming through here. Again, we're just starting to do the sort of verification of this system. So very early on, but we're very excited about it. So, but once we get the verification stuff, how do we get to a car? Ideas of basically we want to bring in additional initial conditions into this system, things like snow cover, soil moisture, that sort of thing. We'd like to extend the forecast out to 12 months. We're tossing around ideas right now of how to best do that. And then we want to basically add more modeling approaches, sort of diversify the NBS itself. Those modeling approaches can be different sort of machine learning algorithms themselves, different methods of doing that. And then the other big thing is we want to continue to engage with our operational partners and stakeholders in this because they've been really helpful in determining what's going to work best for us. So finally, I just wanted to quickly say, how do we as Great Lakes scientists evaluate some of these models? As I've mentioned before, our observations are very limited in the region. We are a bit on a data island, especially in the winter months. So verification is often difficult, but I will say some of our preferred output from models is basically skin temperature. We want to see how that lake surface temperature is being initialized, and on a secondary from that, basically how do you have sort of your surface heat fluxes coming out of the model? What do those look like? Because those are sort of keys on if that system is being sort of modeled correctly. And then also is the ice cover evolving correctly over time? I'm right at time here, so I'll leave that there and happy to take any questions.
No, I have one. So when you're using CFS in your application, what's the largest challenge you have so that we can avoid developing SFS?
Again, it's CFS has been fairly easy to work with. It's getting the data streams correct and getting those easily pointed to with the model so we can download it easily and do the aerial averages. But for the most part, we can pretty reliably use CFS data. So.
Thank you.
Yeah.
So our last but not least speaker is Jon Gottschalck from OER-PSCR. Jon will talk about developing a S2S forecast system for predicting U.S. coastal inundation risk. Jon, please.
All right, thank you for the introduction. I'm Jon Albers, but I'm part of a larger group at the Physical Science Laboratory, and we're working with the National Ocean Service. And the results from today are involve all of these folks, but I just want to point out that in addition to this, the collaboration involves other folks at the National Ocean Service and in GFDL, for example. So For those of you who don't know, I just want to quickly define what high tide flooding is. This is not flooding, from hurricanes or anything like this. This is just a sunny day maybe, and high tide comes in. Maybe that's involved with, sea level rise due to climate change, due to maybe there's onshoring winds due to a persistent NAO pattern or something like this. And then you get, just sunny day flooding like this. And this is a big problem for anything from you can't drive on roads to infrastructure deals very poorly with being inundated all the time with salt water. So part of the problem here is that these types of events are increasing a lot. So on the left is a map of relative sea level rise for the different gauge stations. You can see it's going up pretty much everywhere. You might think Alaska's a standout there, but that's not. That's due to vertical land motion. So sea level is a little bit more difficult to deal with there. But the issue here is that minor flooding used to occur rarely, and now, as you can see from the probability distribution of flooding events, minor floods are happening a lot more frequently, and moderate to major floods are happening measurably more frequently. So this is a problem, and what we would like to do is to collaborate with the National Ocean Service and introduce kind of stand-up forecasting system on subseasonal to annual timescales, so that we can predict coastal inundation risk at all, U.S. coasts and islands, I should point out. So what is currently being done at NOAA co-ops? So for all the U.S. coastal gauge stations, there's essentially a threshold that's based on observations of the historical record, and you have a still water level, and if you have exceeded that still water level, you're in high tide flooding. Currently, the outlooks are made up of a tidal component, a trend component, and a non-tidal residual. That non-tidal residual includes parts, statistical approximations based on observations from the seasonal cycle, high frequency anomalies on hourly timescales. That's essentially a bandpass filtered portion. And then the forecast itself is damped persistence of the monthly anomalies. So that's really the part I'd like to talk about today, because that's where we'd like to insert subseasonal to annual forecasts from climate models and empirical models. All right, so the first question is will current guidance, if we just took something off the shelf, will that help? Will that be better than what we get from damp persistence? The second question is a couple climate models are pretty coarse, right? So, ocean resolutions, depending on what time scale you're talking about, anybody anywhere from 25 to 100 kilometers. End users would like these things at 500 meter scales eventually, which is very high resolution, particularly if you're running ensembles of forecasts up to 2 years. So we have kind of looked at a stepped process to this to get something up and running right away, and then also testing things to look to the future. So the first thing you could maybe do, the simplest thing would be just to take an off-the-shelf forecast product, say from the IFS or the CFS, and take a nearest neighbor approach, or even just do some sort of statistical downscaling. Like NEMOs run at 1/4 degree, and so you just take that as your forecast. Other approaches are, you would do some sort of dynamical downscaling, and I'll touch on that towards the end of my talk. So if you were going to use a nearest neighbor approach, essentially what you're saying that the open ocean forecast is going to be good for a gauge station point forecast. So what I'm showing here is this is the week 3 forecast. This is an anomaly correlation scale for the IFS. It's scored against glories for the open ocean, and then the actual gauge stations for the dots. And what we see here is that there's for most gauge stations, there's pretty good correlation between the open ocean scale and the gauge stations. For example, if you look in Southern California, they match quite well. So, some places where, as I mentioned, Southern California, we do quite well. This is, likely due to, say, coastal Kelvin waves that propagate up, from Baja and give you a lot of skill. Other places we're struggling a bit more, though in the open ocean, for example, it's obviously the loop current is not being done particularly well in the Gulf, but along the coast, we're doing, relatively okay there. Other features that you see where we have some difficulties are on the East Coast, where the Gulf Stream separates. But in general, you can see that this approach holds promise. So what is the versus damp persistence? How are we doing? What I'm showing here are gauge station forecast skill for the IFS for the West and East Coast. And what you probably can't see those are lists of gauge stations from top to bottom. On the left, that starts up in Washington and goes down to San Diego at the bottom. and on the right panel that starts up in Maine and goes down to Georgia. And these are the 6 columns going left to right for each of those are the forecast leads. So this is week 1 through 6. And the raw skill are the left columns, and then the difference are the right column with what is currently just the damp persistence, right? And what you can see is just right off the bat, taking a nearest neighbor approach, we will hands down be improving forecast skill just by inserting this off the top. The one place you'll notice where this doesn't work is you'll notice on the left side there, the blue columns where the skill is actually negative compared to damp persistence. That's to be expected. Those couple of stations are far up the Columbia River, and so obviously an open ocean forecast for those is not going to work well. So with that in mind, the other possibility here, and something that we're currently working on, is doing dynamical downscaling. So we're taking 2 different approaches to this currently. For example, I just put, this is a small subset of what we're doing, but these are just examples, where we take the GEFS V13 output that goes out to 5 weeks, and then we use ensembles of that to drive ensembles of the schism model, which is a higher resolution coastal model for small coastal domains, and we'll have to do that for different domains from the US coast. Keyword there being ensembles, which is going to be expensive. So another thing that we're exploring here is machine learning methods to build, like, say, coastal emulators of schisms, so that we can drive probabilistic guidance, because all of these things need to be done so for subseasonal to annual timescales. It's possible that that's not going to quite work, because you're going from, 1/4 degree ocean to very high resolution and schism. So another approach that we're working on here is doing that in 2 steps. For example, you could take something like the UFS, or the GFDL spear model, and then you use, like MOM6 on a 12th degree, or something like that, to drive a regional domain. And then from that, you have to take another step to go into schism to get down to the smaller coastal domains. And that's something that we're currently working on. So those 2 different approaches need different inputs from forecasting centers. For the nearest neighbor approach, which we're just taking right now, it's pretty simple. We just need sea surface height. We need mean sea level pressure so that we can compute the inverse barometer effect. And then we need the global mean SSH so that we can account for steric and barostatic effects, which is more important on the seasonal timescales, but we in principle, we need for subseasonal timescales as well. To do the dynamical downscaling, we need additional variables, and I've listed those in a table. I don't want to belabor those, but I wanted them in my slides so that folks that are interested in this could see it. I want to stress that both approaches require, we need the models to assimilate satellite altimetry, because we need accurate initial conditions to make these models work. We need some measure of the global mean SSH. We've done some studies. If you don't include that, particularly at seasonal timescales, you're really limiting your forecast skill. And inherently, this is a probabilistic issue. So for all of these things, computation is going to be difficult, because we need to do a lot of ensembles, both not just from the atmospheric side, but when we're driving those, say the 2-step process that I was talking about, for getting it down to eventually 500 meter spatial scales. So, and then you can't wait, see here, there we go. A future wish, which I know is way into the future, I'm saying this to the developers here, is an ocean model that is non-Basin-esque. That we think would really, help with predictions. I know that the models, when they were developed, we're not thinking about having to predict SSH, but now that we are, having a non-Basin-esque model would really be helpful, I think. So with that, I will just leave these key takeaways up there. The current guidance that has the damp persistence forecast for the high tide flood outlook is at that website. That's where eventually we will be segging the new forecasts in, and that's where the forecast outlooks will officially be. And this has been, we're hopeful, because just right off the top, as I said, we're getting a lot of skill just with the products that we have, and moving forward, we're hopeful that the additional approaches are going to allow us to get down with some scale, particularly at the subseasonal timescales. The seasonal timescale is proving to be a bit more difficult, but on subseasonal timescales, I'd say, 6 weeks, right off the bat, we're hopeful about being able to have a lot of value added for stakeholders in this arena. And with that, I will take any questions, or everyone can have a few minutes back for their life.
Very nice to see this application. Regarding your wish list about the non-wish list, I guess if I were to think my wish list would be different. So what about, what would you put, like including the inverse parameter, or having a couple of times, or having a storm surge models? How would that compare with the non-wish list?
Yes. That's a really good question. I would probably put those first, right? Because those are things that I think will probably be feasible in the near future, and getting to a non-looseness model, right? That's a pretty massive endeavor. So yeah, I would put those first. I know that it's not just the barometer effect, but getting the dynamical effect into the model. I think that would be, yes, important. And I know that that's a heavy lift on its own. So.
If there's no other question, we're set to jump. Yes.
Thank you.
Session. So since hours once more again.
Hi, we'd like to use this opportunity to take a group photo outside of the building before the coffee break. So it would be nice, as organizer, we'd like to take a photo of this. Can everybody gather outside?